we can define what continuity of a function is at a point by using limits. We say that a function is continuous at an interior point of its domain if the limit as x tends to that point of f of x actually equals the value of the function at that point. What that's doing is just guaranteeing that if we have some point c, then as the inputs approach c, this is the actual value of c here, so this is what comes out at c. As the inputs approach c, whether from the right or the left, we're just guaranteeing that the outputs will get closer and closer to that actual value of the function. So here's an example of continuity here. This function, you can see you can only take the square root if the number's positive, and so you have to keep the x value between -2 and 2. If you go beyond that, then x squared is larger than 4, and so it's undefined. But so the domain of this function is from -2 to 2. If you pick any point in that range, any point here between -2 and 2, and plug that value into the function, you can see that as the inputs get closer and closer to that value, the outputs are getting closer and closer to the actual value of the function at that point. So it's continuous at the interior. Now we have a little bit of problem at the endpoints of the domain. So here at 2 and at -2, we can't have a full limit as x tends to 2 because as the inputs tend to 2 from above, the function's not even defined. So we don't have a full limit. On the right end of the domain, we have a limit from the left, and at the left end of the domain we have a limit from the right. So if we want to talk about continuity at the endpoints of the domain, we add a little bit here. So we say f is continuous at a left endpoint A, or continuous at a right endpoint B, if you're talking about a left endpoint that the limit as you go to A from above exists and is equal to the value of the function at A. If you're talking about a right endpoint, so B is over here on the right, if you have a limit from the left that's as you approach B, if the values that come out of the function get closer and closer to the actual value at B, then we say it's continuous at an endpoint. So we go down to just having the appropriate sided limit at an endpoint. So in this case, you can see that it's continuous at this right endpoint too, because as the inputs get closer and closer to 2, the outputs get closer and closer to the actual value of the function at 2, which is 0. It's pretty steep there, but it is true that the limit as x tends to 2 from below of f of x does equal f of 2, which is in this case 0. So also on the left endpoint, the limit as x tends to -2 from above of f of x is equal to f of -2. So it's continuous at the two endpoints of its domain as well. Sometimes the best way to think about continuity is to break this definition up into three things that have to be true. First of all, you have to be able to plug the number in, or you have to be able to find f at your particular point C. You also have to be able, so it has to be defined at C. You also have to be able to find the limit. Now, one way to check if the limit exists, sometimes it's helpful to think about the left and right hand limits. So if we're talking about at an interior point, if we can check the left and right hand limits, if they both exist, then you know exist and agree, so they have to be the same. They have to agree on the value of the limit. If they both exist and agree, then the limit exists. So, and then the final thing is that what the limit is has to agree with the value of the function. We could look at a couple examples of functions that are not continuous at a particular point and see how one of these three things would have to fail. And our first example would be something that's kind of familiar to us, f of x equals sine x over x. Now, you can see immediately that it's discontinuous at 0 because f at 0 is not defined. So f is discontinuous at x equal 0. This is my little abbreviation for US. So I just write an S kind of up with a little line under it there. Okay, now that's really not too bad of a problem. The good thing is that the limit does exist. So if we take the limit as x tends to 0, we've seen several times that that limit is 1. So we could fix this function up pretty quickly. All we'd have to do is give this function a good value at 0. So if x isn't 0, we'll continue to use the old function. But if x is equal to 0, if we define that value to be 1, then this new function g is continuous at 0, because the limit as x tends to 0 of g of x is this limit, which is 1, and the value of g at 0, we've just set it up so that the value will be 1. So what we've essentially done is to fill in this hole in the function. Now we get a nice continuous function there. Some functions can be patched up pretty easily. All we have to do is change the value at a single point. Or you could say what we did is we had a function that was continuous everywhere but 0. We extended it to a function that was continuous everywhere including 0. We say we extended it because we made a new function that's defined on a larger range there. Or a larger domain, I should say. Okay, this function has more serious problems. Remember, this sine 1 over x, as x tends to 0, 1 over x gets larger and larger and larger, and so all of the oscillations that sine does as it goes along get packed in so that we have infinitely many. So in this case, the limit as x tends to 0 of f of x doesn't exist. You can't point to one number that the values are getting closer to. It's actually oscillating back and forth so rapidly that just knowing that the input is close to 0 doesn't tell you anything about where the output might be. So some of the outputs that are very close to 0 will be very close to 1, others will be very close to -1, others will be close to numbers in between. So we just don't have a limit here, and so f is discontinuous. Actually, I guess this function has another problem, and that's that f of 0 is not defined. But that, in this case, we can't fix that problem. Last time with the sine x over x, we just adjusted the function a little bit or gave it a value at 0. But even if we were to take this and use this function when it's not equal to 0 and try to extend it to 0, no matter what value we pick here, we could pick -1 or 0 or 1, the limit still doesn't exist, and so it's still going to be discontinuous. You have to have the function has to be defined, the limit has to exist, and the two have to agree. Here's another example. You can see the problem here is again that at -2 the limit doesn't exist, because as you approach -2 from the right, you're getting out values that are closer and closer to 1. So the closer I get to -2, the closer the outputs will be to 1. On the other hand, if I approach -2 from the right, the outputs are approaching -7. So this problem, the limit doesn't exist. So f is discontinuous at -2, because even though f of -2 is defined, it's -7, the limit as x tends to -2 doesn't exist. It's because our left and right hand limits, although they exist, they don't agree, and so the full limit doesn't exist. You need the limit to exist and be equal to the value of the function at the point for it to be continuous. One last one here. We have a function f of x. This one is not continuous at 0. The limit exists at 0. So if you take the limit as x tends to 0 of f of x, that's just the limit as x tends to 0 of sine x over x, which is 1, but that's not the value of f at 0, because the value of f at 0 is 0. So we can have the function can be defined, and this one is defined at 0, and the limit can exist, but if the two don't agree, then it's discontinuous. So f is discontinuous at 0. We've already seen the way to fix that. If you don't mind adjusting the function at this one point, it will now be continuous. So what we've done is basically move this up to plug that hole so that we have a nice continuous function across there.